Good evening, everybody, and welcome to the webinar from the Florida Institute of Technology, Penguins, Polar Bears, and People, Climate Change and the Future of Marine Life. I'm Rich Aronson. I'm a professor of biology at Florida Institute of Technology, and I work on marine ecology and geology, and I'm trying to project the future of marine life using paleontology and ecology together. With me is doctoral student Ange Zamora Duran. She's going to be helping you with some of the questions that you may be asking. So before we get started, I'd like to do a little bit of housekeeping, just a couple of points. The presentation part of this, that's the slides and my commentary, are going to run about 40 minutes, and then once we're done with that, we'll jump right into the questions. If you have any questions or comments that you want to make or that occur to you during the presentation, please feel free to type them into the question window, and then we'll either answer them during the presentation or in the question period later. The presentation is going to be recorded, and so you should look for an email in the next few days that has both links to both the slides and to the recording. So with that, I think we're going to get started. Climate change, of course, is a very hot topic these days, no joke intended. And there is a lot of controversy both about what the facts are and about what we ought to be doing about it. And so I'd like to just lay some groundwork about climate change and then tell you a few things about the impacts of climate change. So first we'll talk about the actual numbers, what we know about climate change, and then we'll talk about some of its ecological impacts. So first of all, climate change is real. We know with data, we know for a fact that air and sea temperatures are rising, we know that sea level is rising, and we know that the ocean is turning sour, which is to say it's turning more acidic as we go along. And we'll talk about all these things as we go along. We also know that humans are causing the preponderance of this climate change by emitting greenhouse gases like carbon dioxide and methane and a few others, and the human element in forcing is real and it is substantial. So just as one example, in the Arctic, half of Arctic warming is caused by human activities and the other half is due to natural variation. So that's a pretty big contribution of human activity. This is the first of a series of data slides to show you what the data actually look like on climate change. We know that the amount of carbon dioxide, which is the primary greenhouse gas that traps heat in the atmosphere, we know that carbon dioxide is increasing, and we know that it hasn't been at a level this high in at least 400 or 600, 550 or 650,000 years, as it says right here. So this, through the glacial cycles up and down, carbon dioxide has maintained a level below 300 parts per million in the atmosphere, and now all of a sudden it's just shooting up towards the sky. So that much we're certain about. And we also know that carbon dioxide is a powerful greenhouse gas, and the way the greenhouse effect works, it's named after greenhouses that are used to grow plants. Basically, in a greenhouse, sunlight comes in through the windows, and when it hits the surface of the plants and the bottom of the greenhouse and so on and so forth, it's radiated back as heat, and then the glass traps the heat, so the greenhouse gets warm. So even in the wintertime, if you're in a greenhouse, it's much warmer than the air is outside. The same thing is true overall for the planet. Carbon dioxide traps the heat that's being re-radiated. So sunlight comes in, it's light, it comes through the atmosphere, it hits the earth, and then part of it is re-radiated as heat, bounces back as heat, and the carbon dioxide and other greenhouse gases trap that heat and warm the planet. This graph shows the relationship between carbon dioxide levels and temperature. So if you look at the line here, this is carbon dioxide levels, and if you look at this bar graph with these blue and red bars, that's showing us the global temperature, and the height or the depth of these bars is relative to this average from 1880 to 2013. So blue bars means it's cooler than average, and red bars means it's hotter than average. And of course, very few years is it actually going to be right on the average. So what do you see here? Well, from 1880 to about the 1930s or 1940s, it's cooler than the overall average over this period, and the balance shifts as you move towards from the 1960s onward to right now, where it's just really quite a bit hotter. Scientists who work on climate have tried very hard, and they've succeeded in parsing out the contributions of natural variability and the contributions of humans to climate change overall. And if you remember at the beginning, I said that half of Arctic warming is due to human activities. This is for the entire globe, going from 1900 to the year to the year 2010 or so, or moving up to 2015, excuse me. And the red line is the human influence, and the blue line is without the human influence. So if humans were not forcing the climate by emitting greenhouse gases, the global temperature would be steady or possibly declining a little bit, but with the human influence, it's actually going in the opposite direction. And a lot of people think, well, we're in a glacial cycle, so there's glaciers and there are interglacials, cold periods and warm periods. Right now, the bottom line is that at this point in the glacial cycle, it should be getting colder, but in fact, it's getting warmer, and that warming is due to human activities. And then these little light gray lines are the impacts of volcanoes, which temporarily cool the planet because the ash reflects light. Okay, there are a bunch of different greenhouse gases. This graph just shows a few of them. They're not all the same in their influence. As it says here again, the influence depends on their ability to absorb radiation. So the position of these dots up and down vertically is their ability to absorb solar radiation. The second factor is how much of that absorbed radiation they emit, and that's the size of these circles. And then the last factor that's important is how long these greenhouse gases stick around. So carbon dioxide is the largest by volume of the greenhouse gases, so it emits the most temperature-wise. But methane is a much more powerful gas greenhouse gas because it absorbs and emits radiation a lot more dramatically than carbon dioxide. And there are other things like nitrous oxide. This is black carbon, it's soot, and it both absorbs and reflects sunlight. Overall, there's no doubt that the climate is warming. This map shows the change in surface temperature over land, that's to say over the continents, and then also over the oceans from 1901 to 2012, just a few years ago. And the more red and purple the little cells are here, the greater the trend of temperature increase. So these purple areas, so over Asia, a little bit over Canada, some in South America, and so forth, those areas have increased in temperature the most. A second issue with climate change for the oceans is that as the oceans warm, they're also soaking up carbon dioxide. Carbon dioxide is slightly dissolvable in the ocean, so as the amount of carbon dioxide in the atmosphere increases, some of that gets soaked up by the ocean. This is the carbon dioxide record from the top of the Mauna Loa volcano in Hawaii. It's been going up very steadily since actually long before 1958 when these recordings were started. But what you see here is an increase in the partial pressure of carbon dioxide in the ocean. That's the amount of gas in the ocean that's dissolved in the ocean, and then so that's increasing, and then pH, which is a measure of acidity, is declining, and lower pH means that the ocean is more acid. So trying to put this all together, there are so many factoids, there's so much information, and there's so much data available that I thought it would be really helpful for you as well as for myself to try to put together all these facts and make some sense out of them and let you know about them. So first of all, the concentration of carbon dioxide. It's projected by 2100, it's projected to be somewhere in the range of 430 to 1,000 parts per million in the atmosphere by 2100. The pre-industrial level is 270. We've already passed 400, so we're well on our way. So we could be seeing a 3 to 4-fold increase in the amount of carbon dioxide in the atmosphere by the end of this century, and that is a lot. Temperature, and comparing temperature, projecting it to 2100, comparing with pre-industrial levels, first of all, you should know that the oceans absorb 93% of the excess heat. So the more heat that gets absorbed by greenhouse gases, the more, of course, is going to be absorbed by the ocean. So it goes from the atmosphere into the ocean. Global temperatures are projected to rise from 2 to about 5.4 degrees centigrade, which is about 4 to 10 degrees Fahrenheit. That is a lot. If you think about the difference between what the average temperature was of the Earth during a glacial cycle, during an ice age, compared with between ice ages, it's only a couple of degrees. So we will exceed the difference between an ice age and the times between ice ages. Sea temperature rise is going to be on the order of half a degree to 4 degrees centigrade, or 1 to 7 degrees Fahrenheit. That is a lot, and it's going to have some massive implications for marine life. Okay, so that's carbon dioxide and temperature. Sea level is also going to rise, and sea level is going to rise for 2 reasons. First of all, high temperatures are going to melt the ice sheets at the poles in the Arctic and the Antarctic, and 2/3 of the sea level rise are predicted to be coming from melting ice sheets. Another third will be from the thermal expansion of water. Well, what does this mean? Everybody says, and it's basically true, that you can't compress water. You can't make it smaller by putting pressure on it. You can't make it smaller by cooling it before it freezes, but that's not completely true. It does expand and contract a little bit as you heat and cool it. And a little bit of expansion in the ocean, which has so much water in it, is actually going to make a difference to sea level rise. So 1/3 of sea level rise we're expecting, again, from thermal expansion of the water, 2/3 from the melting of the ice sheets. Right now, the rate of sea level rise is 3.3 millimeters a year, and by the year 2100, what we are expecting is a sea level rise of 1/3 of a meter to a meter, something like that. That's just adding it all up. And that's to say about a foot to maybe 3 or 4 foot rise. Now, again, you might not think that's a lot, but it is a lot. That's certainly enough to inundate Miami and lower Manhattan and a lot of places. And in fact, we're already seeing fair weather flooding in Miami. Okay, just to bring this whole sea level rise thing home, this is a shot of the Hubbard Glacier in southeastern Alaska. My son took that on a recent vacation we took, and it's a wonderful shot because it's the Hubbard Glacier. This is the front of the glacier, and you can see it turns around through this valley. This glacier is enormous. It goes all the way east to the Yukon Territory in Canada, and this is a gigantic cruise ship. This cruise ship is 12 stories high, and it's sitting in front of this glacier. And like glaciers all around the world, big pieces of ice are coming off that glacier. And so this is a calving event. If you look, this is the height of the height of the front of the glacier. It's 400 feet high, and I just put in this silhouette of the tower of Big Ben for scale. This is a small a small calving event, a bunch of ice filling, and just look at this splash. So if Big Ben was sitting here, the splash would go halfway up to up this tower, and there is ice coming off all the time. So you can sit there for an hour and easily see 5 to 10 of these calving events. So it's happening. This ice then floats out to sea and it melts, and it contributes to sea level rise. Okay, so another thing we need to worry about, as I alluded to before, is oceanic pH. That's to say, the acidity or how sour the ocean is. So for background, you need to know that pH is expressed on a log scale. It's actually a negative log scale. So the lower the pH, the more acid is whatever it is you're talking about. And because it's a log scale, if something has a pH of 6, that means it's 10 times more acidic than something that has pH 7. And by the way, pH 7 is the neutral pH. So distilled water has a pH of 7. So what do we need to know? The ocean traps 50% of the carbon dioxide emissions. So all this CO2 that we're burping into the atmosphere, half of that gets soaked up by the oceans. And it dissolves in the oceans, and through a series of chemical reactions, it forms acid. The pH is averaged 8.2, so slightly basic. That's to say the opposite of acid for the last 300 million years. And oceanic pH is currently 8.1. So that means in the last century or so, the ocean has increased about 25% in its acidity. By 2100, we're expecting that the pH could drop to 7.8, which would be another 50% increase in acidity. Now, seawater is going to remain slightly basic, but it's already corrosive to snail shells in Antarctica, and it's likely that it's going to have some impacts on coral reefs and a lot of other organisms that lay down skeletons made out of calcium carbonate. So, what are the consequences of a warming world? And this is talking again about greenhouse gases, warming, and the associated issues of ocean acidification, which will damage corals and is already causing damage to plankton in Antarctica, which is important because that's whale food. Warmer oceans and rising sea level we already talked about, but a lot of other things that we care about, not just because we care about the planet, but because of our personal, because of how it affects us personally. For example, changing patterns of rain and snow, stronger storms, more droughts and wildfires. If you've been near the newspapers or the web or the TV, you'll know that that's happening a lot right now. Higher temperatures and more heat waves. There has been an increase in heat waves over the last couple of decades. Less snow and ice. The tops of mountains that were formerly covered by glaciers are now less covered by glaciers. And lots of changes in the life cycles, migration patterns, and also the distributions, the geographic distributions of a lot of plants and animals. So things are already changing rapidly. This is not about predicting what's going to happen 50 years from now. It is already happening now. Okay, polar bears. This is one of the more significant, or I should say more charismatic examples of what's going on. If polar bears, again, forgive a silly expression, polar bears are in a way a canary in the coal mine, telling us about what the impacts are going to be of climate change. And here are two beautiful polar bears sitting on the snow. They look very cute. Having seen them in person up in Manitoba, I can tell you they're not very cute. They're terrifying, they're vicious, and they make their living by eating seals, and I'll tell you more about that in a second. Polar bears depend on sea ice, which is this kind of light grayish, very light grayish field up here. This is the Arctic, there's Greenland, there's Canada, this is Hudson Bay, where I actually went to go see polar bears. they depend on the sea ice for feeding because they have to go out on the sea ice and catch the seals that they eat. And September is the month when sea ice extent is the lowest. This is what it looked like in 1979. So lots of the islands in northern Canada still covered with sea ice, a lot of Greenland. And if you look in 2015, it's quite different. All this area is wide open. So sea ice has been declining pretty substantially in recent decades, and this is a plot of what sea ice has looked like over the last few years. These black dots and the black line represent the mean volume of sea ice in the Arctic from 1979 up through 2016. So that's the baseline. What we talk about is the baseline, and then this dark gray is the 50% confidence limit or one standard deviation, and this light color is 2 standard deviations or the 95% confidence limit. So we're 95% confident that that the actual volume of sea ice falls within this gray area, which is to say it does actually follow this pattern of going up and down. So sea ice is the highest in April. It's the lowest in September. Anyway, the important thing is that each of these colored lines represents the cycle of sea ice in a different year. And if you look at the different years, these are the color codings for the different years. If you look at that, what do you see? Well, you see that in general, as time moves on, the amount of sea ice gets lower and lower and lower. And over here in 2017, sea ice is mostly outside of the 95% confidence interval. In other words, it is way out of bounds. It's much lower than you would expect from the long-term average of 1979 to 2016. Okay, well, how does this affect polar bears? Polar bears feed on seals that they catch from the sea ice. So they go out onto the sea ice and they find seals, they grab them, they bite them, they kill them, and this is not very nice to say. They tear their skin off and they eat the blubber of the seals, and they leave a bloody, disgusting, messy carcass behind, which other polar bears and Arctic foxes and a lot of other animals then consume as scavengers. Polar bears depend almost exclusively on seal blubber, not just for their energy, and of course fat has a lot of energy in it, but also for their fresh water. They metabolize or break down the seal blubber to get their water. The amount of time that polar bears have to feed depends on the length of the sea ice season. So if the sea ice is there, they can go out and feed, and if the sea ice is not there, they're stuck on land. So hunting season runs from November to June. That's when they can get out on the sea ice. When they're on land, they don't eat much, maybe a goose egg or eat some kelp as junk food, literally. But they are basically fasting from June to November. So that's their life cycle. And if you look at the number of fasting days, the amount of time that they're fasting, and how much mortality they have, how much, in other words, the more they're starving, the more they're going to die. And if in the 1980s, they were fasting for around 120 days a year, and the mortality from starvation was 3%. Since the 1980s, the average loss of feeding time has been a day per year. So that means in 30 years, they've lost a month of feeding time. That is a lot. So in the 2010s, they had about 150 days, leading to a 10% mortality rate. In the 2020s, we're expecting a 20% mortality rate. And in the 2030s, we can expect something in the neighborhood of 25 or 28% to perhaps up to 50% mortality rate. This is why polar bears are considered threatened under the U.S. Endangered Species Act. Okay. Moving on to some other other impacts of climate change. As it gets cold in the Andes, oh, sorry, excuse me, as it gets warm in the Andes, the forests are going to start migrating from lower elevations to higher elevations, because the plants that live in these forests, the trees and the shrubs and all that, they're going to follow the habitat of their preferred temperatures. So they're going to start moving up. And so you might think to yourself, well, no problem, they're just going to move up. What's the big deal? Well, the big deal is that, as everybody knows, mountains are pointy, and the Andes are particularly pointy. And once these forests wind up at the tops of these mountains, they're just going to run out of area, and eventually they're going to wink out. In Antarctica, another charismatic animal is having a rough time with climate change, and that's the penguin. There are several species of penguin, and the ranges, the geographic ranges of these penguins are shifting southward as it gets warmer. So remember, the Antarctica is in the southern hemisphere, so higher latitudes, colder latitudes are further south than warmer latitudes, which are further north towards the tropics. These cute little penguins, the Adelie penguins, are more cold sensitive than these chinstrap penguins, and they are moving south, and the penguins that are remaining along the western side of the Antarctic Peninsula, which is the part that sticks up towards South America, we're seeing a greater proportion of these chinstraps and a lesser proportion of these Adelies as they have to move south to get their preferred temperature. Well, it turns out that this has a lot to do with food supply, temperature, and habitat. And it's a complicated story, but one thing that I can tell you is we are figuring it out. But if you take a look at the Adelie penguins, they're just diving along the western Antarctic Peninsula, and the chinstraps are going down too, but not to as great an extent. So the proportion of chinstrap penguins is increasing relative to the proportion of Adelie penguins, but overall, penguins in general are becoming less abundant. And it's due a lot to the amount of sea ice that's available, and that sea ice is where krill, which is their primary food, where they breed, and so the food supply is going down. Coral reefs are another area where we're seeing some big changes. This is a typical coral reef scene. This happens to be from Jamaica from quite a while ago when I first started diving. And you see a number of species of corals, and they're all kind of a yellowish or golden brown color. And the reason they're that color is that they have little tiny single-cell plants living inside their body tissues, and those are called zooxanthellae. And for those of you who like algae, it's a type of dinoflagellate algae. Those plants do what plants do, which is to say they do photosynthesis and they make carbohydrates, and a lot of those carbohydrates leak out of the plant cells and go to the coral animal, which is this sea anemone-like thing. So the coral is a colony of these sea anemone-like animals. They're all joined together, and they secrete a base made out of limestone, which of course is vulnerable to ocean acidification. Just like if you have a crust of limestone from hard water on your faucet, you put vinegar on it. In the same way, ocean acidification could dissolve these skeletons. So all these coral colonies are a very thin layer of living tissue that's this clone of these sea anemone-like things, all joined together and sharing resources over the massive skeleton that's been built up over previous generations of the corals. Well, this is what a beautiful normal coral reef looks like. This is a picture that my colleague Rob Van Woesik took. He's also at Florida Institute of Technology. He's an expert on coral reefs. And you can see that these coral colonies are nice brown color. Everybody's happy, everybody's doing fine. But at times the ocean becomes very hot, and it becomes hot from a phenomenon called El Nino events, and those are now being enhanced or amped up by climate change. And what this series of panels shows, this is a series of maps of the Great Barrier Reef off the east coast of Australia, and this bottom set shows the amount of thermal stress. That is to say, how much above normal is the temperature at different times. Here's 1998 when there was a big bleaching event, 2002 when there was another bleaching event, and then just last year in 2016 when there was just a massive bleaching event. And the point of this is to look at where the red spots are in this graph, which is to say where it's really hot, and compare with the map of coral bleaching, which is what happens when these animal-plant relationships get hot. This relationship of the plant feeding the animal breaks down, and these animals literally puke out these poor little plants, and they blanch because the color of these corals actually is from those little plants. The coral animals themselves are translucent, so they don't have any color themselves. All this color is from the plants that live with them. So bleaching in 2016, it was very hot in the northern part of the Great Barrier Reef, and that's where the preponderance of the bleaching happened. And this is what it looked like in 2016. You can see all these same kinds of corals that I showed you in the previous, in that slide of those nice healthy corals. They've lost all those little plants and they've turned white. Some of these corals have a kind of a natural pinkish hue, but very little of the coral area is that healthy brownish hue. And what that means is that they don't have a food source, and then they are starving. And if they bleach for too long or too intensely, they simply starve to death and they die. So another one. This is Antarctica. It turns out that crabs have been shut out of Antarctica by cold temperatures for probably tens of millions of years, at least, maybe as much as 40 million years. And the reasons have to do with the way they process magnesium in their blood. Magnesium is a narcotic. Crabs just can't flush it out. At cold temperatures, magnesium, they're already moving slowly because it's cold. Magnesium just basically makes them pass out and die. And so that's why for many eons there haven't been any crabs in Antarctica, and the seafloor communities there have gone in a direction that's very different from what we see in seafloor communities in other parts of the world. Well, now we're discovering these crabs all along these areas in Antarctica. They're living in the deep sea right now. There are several species of them. This is an area called the Kerguelen Plateau, and they're in a few other places. And it looks like they're starting to creep up and possibly start creeping onto the continental shelf. And they are predators. There are no predators that crack snails and clams and starfish and things like that in Antarctica right now. These animals do, and the danger is that they will get up onto the shelf as it gets warmer, and they can survive, and they don't get knocked out by magnesium and start disrupting these bottom communities. There are also some crabs from shallow water habitats, a bunch living in southern South America here and elsewhere in the regions around Antarctica. This one, Halicarcinus, doesn't have a common name, has already made it to Deception Island, which is an island very close to the Antarctic Peninsula, so it's already almost there. And that one doesn't have much of an impact on bottom communities, but this one, the green crab, this is the European green crab, Carcinus minus. The European green crab is globally invasive, and it is just sitting there poised to invade. And these two crabs, for whatever reason, just don't have this magnesium problem that I've been mentioning. And so this one's already there in Antarctica. This one's going to be there very soon. So we've got crabs coming up from the deep sea, and we've got crabs coming across. These are predatory. The ones I showed you before are predatory. These are not especially predatory, but these crabs are known all over the world for causing havoc in marine communities. Okay, so that's the biology. That for me as an ecologist and a biologist, that's reason enough to be concerned about this. But what about you personally? Why should you care? Why else should we care? Well, a whole bunch of reasons. First of all, there's the threat of changing weather patterns. More heat waves, stronger hurricanes, more wildfires, and more winter cold snaps. One of the predictions, one of the reasons we now call it climate change and not global warming is that some areas are going to get cold. So the jet stream, now called the polar vortex, that was one of the first predictions of climate change, was that that jet stream would start to wobble, and sure enough, it's happening, and we're getting these crazy freezes in more southerly latitudes, like in the subtropics, like here in Florida. So we've already mentioned some of these before. Threat of rising sea level we've talked about before, but then some more geopolitical and social issues. Compromised food security. The farm belts are going to move northward. Fish stocks are going to change. Certain fish, including ones that we eat, are going to start moving further to the north. And that's going to have an impact because overall agricultural output is going to go down, and overall fish production or fish harvests are going to go down. Compromised water security. One of the things that's happening with climate change that, again, was predicted and that's coming true is that although the total amount of water might remain the same on the planet, where and when that rain falls is going to be much more variable. That is to say, there'll be more areas that are very dry. There'll be more areas that are completely soaked. And during the course of the year, even if the average amount of water stays the same, it's all going to be coming down more or less at the same time rather than being spread out. So that's going to have a huge impact not only on agriculture but on people's drinking water. And in fact, water is going to be the new oil. Water already is the new oil. It's going to be the resource that people will fight wars over. There will be an increased incidence of human, livestock, and wildlife diseases because a lot of the microbes that cause these diseases do better in slightly warmer temperatures. So what are the data showing us? Well, changing wheat production. These are some predictions of changed wheat production over the next century or so. Some areas are going to see increased wheat production, like some areas in Canada, because the wheat belt is going to move north. But if you sum it up over the total globe, wheat production overall is going to go down. So there's going to be less food at a time when the population is continuing to increase. Water. These are some observations of the availability of water from 1980 to 2000 to the best data we have for 2015. And if you look at the colors, the sort of the more yellowish and kind of reddish brown colors are the greater amounts of water stress. And what you can see is that as you move forward in time, there's more and more water stress. So take a look, for example, take a look at India. India, as you know, has a very large population. India is going to be stressed out increasingly by water availability. Projecting, so that's what we know. Projecting to the future for 2025, which is not very long from now, this is what freshwater stress is going to look like. Again, take a look at India here in 1995 and what we are pretty sure is going to be happening. Here you can look at Southern Africa, here and here, that's South Africa. Look at the U.S. then now, and then what we're projecting in the future. There's going to be more freshwater stress. Disease, just one example of many diseases. Malaria, one of the main killers, if not the biggest killer in the world today, is malaria. And we are going to be seeing malaria, the red are the projected by 2050. We're going to see malaria cropping up in the United States. When I was a kid in junior high school, I heard that there was still malaria and there was still some other tropical diseases in Charleston, South Carolina. They've since been eradicated through mosquito control, and malaria is coming back with climate change. We've got Zika, we've got dengue fever, which was restricted to the tropics until recently. It is going to happen, and yes, you should be alarmed about this. Violence. It turns out that when it's hot, people fight more and kill each other more. And this is from a series of studies by Solomon Sang, published in Science and a bunch of other places. And what these researchers found was that at all levels, from the neighborhood, petty crime in the neighborhood, to fights across states and across counties around the world to global, which is a civil war, to global geopolitical blowout wars, they all increase as the climate gets hot, gets warmer, and drought conditions get more severe. And again, they're related, right? The warmer it is, the more drought there's going to be. So we can expect more violence. And if a lot of this sounds like it's already happening, that's because it actually is already happening. Just take a look around you. Of course, I hope everybody reads the newspaper or goes on the web or watches the news on TV. So it's from all of this, it's pretty easy to formulate basically a 12-step program to societal meltdown, and it just goes like this. This is just common sense, and there's a lot of evidence that this is what's happening. Overpopulation, that's the big kicker. That's what gives us greenhouse gases. The more people, the more greenhouse gases are being belched out. That leads to climate change, pollution, and also over-harvesting. So more people need more food. The environment gets degraded. That increases poverty and the economic disparity, by which I mean the difference between poor people and rich people. The difference in income level is increasing dramatically, and not just in the developing world, but also in the developed world. If you're out in some coastal area and you don't have any food and the environment's falling apart, what do? You migrate to urban centers. And what happens there? You wind up in the slums, so expansion of the urban underclass, and that leads to social unrest and radicalization and terrorism. So we Americans are pretty worried about terrorism, and as we ought to be, and there's your route to increase terrorism, again, about climate and water and resources. The response to terrorism is compromised civil liberties as a reaction. Escalated responses on all sides, compromised civil liberties, leads to more unrest, leads to more compromised civil liberties. Global blowout conflict and societal meltdown. Again, I know this sounds horrible. It should sound horrible. This is why we have to control the climate. Okay, climate change and democracy. We live in a democracy. What should we be thinking about and what should we be voting about when we come to think about climate change? First of all, it's important to remember that this country is founded on the philosophy of Jeffersonian democracy. In other words, democracy that was designed by Thomas Jefferson, with all its warts about the conflicts between central government and states' rights and all that other stuff. But leaving that aside, the basic idea is that the people run the country and are not dictated to, but it's the premise of it is the idea that the electorate, the people who are voting, are educated and informed. So that's great, and it's a wonderful system. Right now, people are arguing about climate change, about whether climate change is here or it isn't. We're not supposed to be voting on facts. The facts are what they are. So sometimes people say, well, do you believe in climate change? I don't believe in it. I know it's true. This is based on scientific fact. Scientific facts are not for voting. Scientific facts are for learning. So just as a corollary to that, I've been reading up on climate change on the internet. That doesn't make you an expert on the subject or on any other subject, because you know that there's plenty that's good and plenty that's bad on the internet. Our job as citizens of this democracy, the United States, is to learn the facts of climate change and use them to formulate policy and to vote on policy. We have to make decisions about whether or what we're going to do about climate change. Climate change is real, and it really is, in large part, a result of human activities. The question is, do we want to do something about it? If we're going to do something about it, what should we do? Okay, a second thing, or a third thing, or 12th thing. Some people say, well, it's all happened before, so what's the big deal? Well, whether this happened before or not is really not important. The important issue is the desirability of what's going to happen. It has been warm before, but before there weren't 7 billion people, a lot of whom live below sea level and could potentially get drowned out by rising sea levels. So it's about the desirability, the outcome. And desirability aside, It actually has not happened like this before. Climate change hasn't been this rapid or this wild in at least a million years. Bottom line is that climate change is filled with surprises, and most of them are very nasty surprises. And I do want to say one more thing about prior occurrence. People say, well, it's happened before, so what? Well, another thing that happened before was that 65 million years ago, a gigantic asteroid blasted into the Earth and killed just about everything out there, and you wouldn't want that to happen either. So I'm not so sure I like this whole prior occurrence thing, even on the face of it. Well, what are we going to do? Well, we're going to have to do international cooperation to reduce greenhouse gases. The best model I know was the Montreal Protocol, which entered into force in 1989. That was the ban on chlorofluorocarbons or CFCs to protect the ozone layer. This was based on the ozone hole over Antarctica, which really was and remains a big deal. The ozone hole is closing very gradually. There's just something actually in the news today about the ozone hole. There are some other gases that are going up there that are going to delay closure of the ozone hole, but very gradually it's closing. It opens, it closes, sometimes it opens more, sometimes it opens less, but the overall trend is down. The main point is that the countries of the world got together and took action to solve a problem. So that's our model for international cooperation. Well, while people are screaming and yelling about what they believe, that is to say, trying to vote on facts, a bunch of other concerns are already preparing for climate change. The U.S. military is planning defense for an ice-free Arctic. Who's right opposite us in the Arctic? It's Russia. If it's ice-free, we're right across from Russia, something to plan for. The U.S. military is planning for civil defense in the face of increasing levels of disaster, natural disaster, human-caused physical disasters like massive hurricanes, massive flooding, and so forth. So the U.S. military is on board about climate change, despite what anybody might want to vote on about the facts. Global insurance companies are planning for increased hurricanes. So for example, in Bermuda, Lloyd's of London is thinking about what's going to happen in an era of increased hurricanes and how should they indemnify various concerns. On the religious front, the Pope and other religious leaders are thinking about climate change, and they're looking at the ethical and moral dimensions of climate change's regressive impacts. And what I mean by that is that climate change disproportionately affects poor people. They are less able to protect themselves from climate change. And so everybody's thinking about it. We can argue about it till the cows come home, but if we do that, we're going to get caught up in it. It's like trying to escape a hurricane in your car, getting stuck in traffic, and getting overtaken. So what should you do if you want to do something about climate change? First of all, you have to realize that different people have different stakes in what resources we harvest, the manufacturing we do, agriculture, how much carbon emission there should be, how much there should not be, so on and so forth. First of all, don't consider them evil and don't call them evil. They're not evil. They're just trying to get by. And don't call them stupid. One thing that I've learned as a scientist is when you call people stupid, it hurts their feelings. So don't do that. They're not stupid. Be nice, be respectful, and show some sympathy for their political or economic concerns. And make it worth their while to buy into carbon control. Many years of telling people that we're all going to burn up and die are less compelling, as it turns out, than explaining to people the immediate benefit or profit that they can reap from going green. And in fact, green jobs and green energy are rapidly overtaking petroleum in the energy sector. So it's even we can argue a lot, but it's likely going to happen all by itself, just by pure economics. So it's basically your choice. You can argue, you can try to teach people a lesson, or you can try to save the planet. Teaching people a lesson, that's just just not as worthwhile a thing. We want to get a result. We're not just trying to say nah, I told you so and I was right and you were wrong. That doesn't help anybody. So that's really what this is all about. And what you can do individually is, well, you can become an activist for carbon control. and you can live sustainably. You can use fewer fossil fuels, you can conserve water, you can choose the food you eat, you can eat lower on the food chain, which means less greenhouse gases produced and less energy consumed in making those foods. And you can vote. So use your vote. If you're of voting age, go out and register and vote in the next election and vote in every election. The bottom line is that the window is still open, but it's closing, and we really need to put our arm in there and keep that window open. It's not a hopeless case. If it was a hopeless case, I wouldn't be here talking to you today. And I just will quote Paul Valéry, who was a poet who died in 1945 in France, and you can imagine the things he saw. He saw the worst of the Second World War. He said, trend is not destiny. That is to say, things are looking bad, but that doesn't mean we're condemned to it. And a lot of other thinkers have picked this up and used it. So that's what I have to say to you. And so now I think we can go to questions. Angie's been answering questions along the way, and I'm going to let our tech people start running the show here, and we'll answer some questions.
Okay, so I got many good questions from Jessica Carter. The one that I think would be beneficial to answer first is, how do we know that the climate has changed in the past? And is it just an assumption that it is now changing at a rate that is quicker than what happened in the past?
And we do know that climate, so the question is, how do we know that climate has changed in the past, and is it just an assumption that climate is changing more rapidly now? No, it's we do know how rapidly it's changed in the past, and the way we reconstruct climate is by collecting cores, which cores from the deep sea that have little tiny shelled amoebas in them called foraminifera, which happen to be the subject of Angie's Ph.D. research. And from the chemistry of those foraminifera, those little shelled amoebas, we can actually reconstruct temperatures over geologic time. So we'll use radiocarbon dating or other dating techniques to find out how old these little bugs are, their little shells, and then we can analyze the chemistry of their shells and figure out what the temperature was in the past. That's called a proxy. And then we reconstruct the temperature in the past, and we can do this at a very fine scale, and then we compare that with actual measures of temperature in the modern, and we can see that the rise in temperature, and also we can track the amount of carbon dioxide in those very same little bugs, that the amount of carbon dioxide and the temperature are skyrocketing at a much higher rate now than they have been in the past.
And then another question she asked was about bioengineering, in the sense, can we plant more plants or trees to help lower CO2 levels and produce more oxygen?
Sure, we can do that. One of the best things we can do is to reforest areas. We have to do that in tandem with carbon control. We're only going to solve this problem. We can do as all kinds of things. We can try all sorts of, there are all sorts of good ideas and not so great ideas about well, there's bioengineering, planting more trees. There's also geoengineering, which is actually doing things like dumping iron in Antarctica and trying to create plankton blooms that suck up carbon dioxide and then sink into the deep sea and disappear for 1,200 years and then bother us 1,200 years later. There are a lot of problems with a lot of those sorts of solutions. But of course, the more trees we plant, the better off we're going to be. But a lot of this is about trying to live sustainably, managing all of our resources better than we are now.
And then she asked the question about diseases. So if we know that climate change is coming and diseases will become more prevalent, can we not prepare ahead of time so that these could be eradicated immediately?
So the question is should we be planning ahead for increases in disease? The answer is yes, we should be planning for increasing diseases. The second part of the question is, can we eradicate them before they get here? Well, these are diseases that are already on the planet. People have been working on malaria and dengue and a lot of diseases for a very long time, and we're making progress. But it's not just a matter of saying, okay, well, we'll just cure these diseases and it won't be a problem, because it takes some time to do that. And so you know, again, it's yes, of course, we're going to plan for disease. One of the things we can do is be very vigilant about mosquito control, because a lot of these diseases are mosquito borne. So that, of course, is going to help a lot, at least for us, you know, in the U.S., where mosquito control is a lot more feasible than in a lot of other places. But again, that's responding to climate change. We have to do some adaptation to climate change, you know, changing our lifestyle. But the main thing that we have to do is mitigate or reduce the amount of carbon that we're spewing out into the atmosphere. And quite frankly, even if we stop dead in our tracks right now, it's going to take a while before the amount of carbon dioxide reverses and the temperature stops increasing and slows down and starts to decrease.
A question just came in from Tegla Jones. Is there a potential for climate change to fix itself? Will it reach a point when it will revert back to normal?
So the question is there potential for climate change to fix itself? Climate change, as I said, is full of surprises. Most of those surprises, unfortunately, they're nasty surprises. I don't see any reason to think that this is just simply going to sort itself out in certainly on a scale of decades to centuries.
We had a question earlier from Emerson White, who asked which animal or group of animals is worst affected by climate change, and is there a way to stop it?
So the question is what are the worst affected groups by climate change, and is there a way to stop it? Well, in this talk I showed that there are a lot of different types of animals, everything from corals to polar bears to little tiny snails that live up in the water. They're all being affected by rising temperatures and ocean acidification. Trees are being forced to the tops of mountains where they're running out of space to live. So to say which one is worse affected, there are so many plants and animals that are changing around. Plants are coming into bloom before the insects that pollinate them are coming out of their pupae. Yeah, there are just so many different things going on. So the footprint is there. I mean, if you don't like the chemistry is kind of irrefutable. If you don't like if you don't like the physical measurements, just take a look at the animals around you and the plants around you. I don't see any way to really make a judgment. It's just pick your favorite plant or animal and see what's going on, see what climate change is doing to that species.
And then Jessica asked, are there ways to reuse CO2 from the atmosphere for something else to help reduce the CO2 in the atmosphere?
Well, the way to reuse it is really to make it into trees, and so that falls on the you know, on what we talked about, what a previous question, which was can we plant more trees? Carbon dioxide, if you put carbon dioxide into tree growth or you plant more trees, you will get it being transformed into wood, where at least for on a scale of centuries, it's going to be out of action. So that's one way to mitigate carbon in the atmosphere, reduce carbon in the atmosphere.
Tegla's question, if climate change is not able to be solved, is there a way to adapt?
Yes, there are ways to adapt, and that's one of the things that I talked about. We have to do two things. We have to solve it, otherwise we are going to burn up. But we also have to adapt at the same time. So, for example, if you live near the shore, we're going to have to, at some point, do managed retreats from living near the shore, because the shore is going to, let's just say, if we're a few blocks from the beach, we're going to be beachfront within a few decades. So we do have to adapt. We have to change the way we do things. We're going to have to live right now with more strong hurricanes. We're going to have to live with sea level rise. We are going to have to live with a lot more heat waves, and and deal with, for example, with wildfires like they're having in California. Maybe this means there are some places we're not going to be able to live anymore, like low-lying areas, low-lying like in estuaries and deltas. Maybe we just won't be able to live there. So that's adaptation, and we're going to have to do that to some extent while we work on the issue of reducing the amount of carbon. Again, I'm very hopeful that just by the kind of automatics of the economy, that will be going more and more towards alternative sources of energy.
Megan asked, what would happen if most of the coral reefs all died off? How can we save them?
Well, if the coral reefs die off, coral reefs do several things. A couple of the main things they do is they provide food for 500 million people at least around the planet, and that's from fish and you know, and other things like shellfish. And then they also protect shorelines from the impacts of storm waves. So when a big storm comes, it's the reef that blocks the shoreline from getting eroded, and of course therefore blocks people's houses from getting washed away. So if corals die, then and sea level continues to rise, then first of all, those storm waves are going to be coming in and causing more erosion. And secondly, corals provide the structure. They're like cities, like buildings in a city. They provide the structure where the fish hide. So when the corals die, they start to fall apart, the reef gets flatter, and you're going to have fewer fish. So that's, you know, those are problems, and the way to solve the issue is, of course, to address climate change first of all, and also to do that in tandem with good conservation practices like well-managed fishing and not harvesting coral and other sorts of other sorts of management actions like that.
Jessica asked, how many trees would it take to reduce CO2 levels if they were reduced?
I am sorry, I just don't know the answer to that.
And then she also asked, is there a way to potentially live on the water or above water?
Well, people do live over the water in houses on stilts. That's the kind of actual something that you actually see. And of course, there have been a bunch of movies and novels about people who are living a kind of an existence on these giant floating cities and that sort of thing. That's kind of fanciful science fiction at this point. But yeah, I mean, we're going to have to make our living and make our way a little bit more in a little bit closer association with the water, I think.
Robin asked, would climate change have such an impact on the Earth if there was little to no human impact whatsoever? Would it still be a major issue if humans were not an influence?
That's a great question. The question is, would climate change have an impact on the Earth if humans weren't around? If humans weren't around, the climatic cycles would be driven primarily by the way the Earth orbits around the sun and its angle with respect to the sun. And so there would be natural cycles of warm and cold. And one of the things about those cycles is, compared with what's going on now, is that they run at a slow enough pace that the animals and plants and the communities in which they live adjust more smoothly to changes. Right now, things are happening so rapidly because of human impacts that they're outpacing the ability of any of these organisms to respond in any sort of effective way. So things are going to change, and just to say that things are going to change is not in and of itself a big deal because things change all the time. But again, this is a question of desirability. How is this going to have an impact on us as animals that need to eat and need to survive, but also as this strange animal with a moral sensibility and some ethical some ethical stake in how the planet runs. And I think with that we should probably finish up, if that's
Veronica did
good.
have a good closing.
Oh yes,
question.
okay.
What other resources do you recommend to learn more about this topic?
To learn more about this topic, there are some good web resources. Not everything on the web is wrong. Of course, there are a lot of good things. I would look at, for example, look at the website of the National Oceanic and Atmospheric Administration. That's NOAA, and there are a lot of other websites. There's NCAR, the National Center for Atmospheric Research in Boulder, Colorado. There are a few around there that will give you some really nice graphics and some really good illustrations and some good numbers that you can use to talk about climate change. And of course, this webcast is going to be available. So of course, I'd be delighted if you use some of those summary slides that I've put up as well. Well, with that, thank you very much, and I think we'll end it here.